For our second reaction mechanism, we finally were able to do what we wanted to do in reaction mechanism 1, which is to convert a carboxylic acid and an amine to an amide, but we're only able to do so when we chemically activate the carboxylic acid by converting it into an acid anhydride. And just to highlight here, if you ever have any questions about what I'm asking for in terms of the starting material or the product, please, come see me. But again, by having these video solutions posted, hopefully it's not anything that kind of gets in the way of your ability to do the mechanism. You could just watch the beginning part of it just to get the starting materials and then work through the mechanism on your own and check your answer by completing the video. But again, we start with an acid anhydride. So an acid anhydride looks like this. And I'm going to distinguish the left and the right rest of the molecule, the R and the R prime, by having that prime there. But again, I'm just going to highlight that attack on either of those carbonyls in solution would be accurate, whether it's the carbonyl on the left or the carbonyl on the right. In solution, there's really no distinction between them. So we're going to have our amine here. I'm just going to distinguish that R group as being separate in that way. We're going to have nucleophilic attack now on that carbonyl carbon, generating our tetrahedral intermediate. Making sure we show all relevant atoms and lone pairs. Again, we're going to have a positive charge on this protonated amine, negative charge on what was the carbonyl oxygen. And what we may have shown in the past was just PT in order to indicate a proton transfer. In this case, we're actually going to show solvent doing the proton transfer, essentially deprotonating the protonated amine, which we don't want to be a good leaving group. And so we're going to show again a base, and we generate base just with a B with a semicolon to indicate the lone pair on that basic atom. And what we're going to actually show up here as well is we're going to show a protonation of that oxygen atom on the tetrahedral intermediate. So again, protonation here, deprotonation down here, generates our carbonylamine intermediate. So again, this guy here, we're going to abbreviate TI for tetrahedral intermediate. When we kind of move and shuffle these protons around, we generate what's called a carbonylamine intermediate. So we'll draw it out here, and then we'll see why it makes sense that it's given that name. So everything here is neutral, which again is going to be a much more stable species than if everything was charged as we had before. So again, this is a carbonyl amine intermediate. No charged atoms, so it's going to be more stable than the tetrahedral intermediate. And again, that tetrahedral intermediate had this protonated amine being the best leaving group. So it's actually going to be better here when we eliminate and deprotonate that protonated amine. Kind of continuing with our mechanism here, we're going to see themes here where we generate our tetrahedral intermediate and then we decompose our tetrahedral intermediate by moving those electrons back down to reform our pi bond. And you're going to break the sigma bond to the best leaving group, which is again going to be your weakest base. And because we deprotonated that protonated amine, now we've got a better leaving group in the carboxylate group. Kind of continuing along here to generate our protonated amide here as one product, protonated on the oxygen of the carbonyl, plus our carboxylic acid here as a carboxylate group. And again, that was just a good leaving group. And finish out here by having a base that can come in and deprotonate this protonated carbonyl. Protonated carbonyls are very acidic, so it's very easy to kind of remove that group. And we're left with our final amide product. and then the displaced carboxylate group. So a couple of things just to kind of comment and highlight on this. And I know there's a lot of words here, so we'll kind of flip back and forth as we talk about each of these bullet points. So building on what we saw in reaction mechanism 1, we can take the carboxylic acid functional group and convert it to an amide by doing chemistry with amines, but we have to get rid of that more electrophilic proton. And so we convert it into an acid anhydride. So again, what we had here is we converted that into our acid anhydride, and now in lacking that electrophilic proton, we can generate our final product. So in general, water can always be used as an acid or a base, using it as H2O, but for a lot of our reaction mechanisms, we're just going to use what we call general acids or general bases. And general acids, we want to kind of highlight and use them in this form. And then general bases, we're going to use them in that form. So again, these are going to be simple ways to show solvent molecules that either act in a proton donation or a proton abstraction form. The last little piece here is, again, noting the common chemistry that occurs with these carbonyl compounds. We're going to see a lot of carbonyl-containing functional groups to do chemistry with, and the first step is almost always nucleophilic attack on the carbonyl carbon, and we generate a tetrahedral intermediate. So that's what we see in our first step. Our amine is our nucleophile attacking our electrophilic carbonyl of our acid anhydride, and we generate this tetrahedral intermediate. If there's a decent leaving group, as is the case here when we have an acid anhydride, what we see is called nucleophilic acyl substitution. And often in organic chemistry textbooks, this is referred to as nucleophilic addition elimination. And this emphasizes the two-step nature of the process, where we've added in our nucleophile and then eliminated the good leaving group. So as we noted in our mechanism, this frequently requires some proton shuffling to make the group that we want to be the best leaving group. And again, after step 1, the amine is still going to be the best leaving group as a protonated amine. So after doing some proton shuffling, the carboxylate can then become the best leaving group and departs after we collapse our tetrahedral intermediate. So kind of coming back here to highlight that, our tetrahedral intermediate is basically still going to have a good leaving group as that protonated amine. So we do some proton reshuffling using solvent in the forms of a general acid and a general base to deprotonate our amine to make it not a good leaving group, and that allows our carboxylate to be the better leaving group. It departs, and then after deprotonation of the protonated carbonyl, we generate our final amide products.